Hi everyone, my name is Genta. Today I'll present our work, lightweight and efficient end-to-end speech recognition using low-rank transformer. This is a joint work in our university, HKUST, and CARE, Center for Artificial Intelligence Research. I will start to cover the background of the research, and then we walk through to the preliminaries and related work. After that, I will explain the proposed model, low-rank transformer, and describe how we set up our experiments and show our result analysis. At last, we conclude and wrap up our presentation. Let's start with the background. Speech recognition has been a major research topic, and many different studies have applied different neural-based end-to-end structures. However, they are usually large in size and they need to be trained in large capacity GPU or TPU. Especially for RNN-based models that require high computational power machines, and it takes a lot of time to train. While the demand of ASR in the technological industry is huge, and those systems are expected to be run smoothly in low-end devices such as smartphone. We have a couple of questions that are important to answer today. First, can smaller models perform better than larger models? It's a common question for people, especially people who study in NLP and speech recognition tasks, that larger models are usually achieve better performance compared to smaller models, but that are not actually true, because small models can also perform better if we have a good method or a smart algorithm to compress the size of the larger model while we also preserve the informations. And the second question is how to compress model without any performance loss, and how to speed up the training and inference time. This is also important questions that we will answer in the end of this presentation, and we will show you that our proposed model can do those things by compressing the model, and also try to make the training and the inference time faster. Let me continue with the preliminaries on metric factorization methods, and later I will explain to you how we apply the factorization to compress neural-based models, and we describe end-to-end speech recognition models to date. So let's start with low-rank metric factorization. Given a large matrix m times n dimensions, we can decompose a large matrix into smaller matrices, such as matrix U and matrix V, where the rank of those matrices is smaller than the dimension of the original matrix. Why this factorization is useful? There are three things. First, when we have a compact and dense matrices, it means that we can save a lot of space, we can save memory, and also we can reduce the floating points operations from m times n into m plus n times r. And with this in mind, in terms of memory and time complexity, we actually can achieve a very efficient models. And then there's one applications or algorithm that has been widely used, which is non-negative matrix factorization. So NMF algorithm aims to find a small r to approximate a large matrix W. And in this case, the objective function of this algorithm is to minimize the probability norm of W minus UV, where there's another constraint that is given to this algorithm, which is U have to be kept a non-negative, and also the multiplication of U and V should be approximate the large matrix W. Now we will describe how factorization can be applied to model compression. There are two model compression methods that are widely used in machine learning. They are in-training and post-training. In-training methods focuses on reducing the model by design, which means we compress the structure of the model before we start to train the model. And the benefits and advantages to have this kind of method is to reduce training time. We have less training time and also low memory cost. And also the model that we train can learn the compact representations from the distribution of the training data. In contrary, for post-training method, it does not reduce the training time or lower the memory cost, but instead it can leverage the existing pre-trained models and by using those existing pre-trained models, actually we can try to preserve and approximate the original models, which is also a useful use case if we have large models such as, for example, Elmo or BERT for NLP applications. One of the example of the study that has been done in 2017 is in training factorized LSTM. So the model accelerates the training of LSTM by applying in-training methods, and the model improved the speed of the training and inference time with a small performance loss. And they introduced methods to partition the weights and also partition the input and hidden states. Another work that has been done for factorization in neural networks, it's been done by our group last year, 2019. We proposed a study to explore comprehensive comparisons on different post-training methods like SVD, pruning, or low-rank metric factorization on LSTM to different NLP tasks such as language model, QA, sentiment analysis, or such as Squad, and also Wikitext and pantry banks. So we found that the low-rank metric factorization generally achieve better performance than pruning, which is a good insights. And then let's move on the end-to-end speech cognitions that has been used recently. There are three main structures. The first one is RNN-based models with attention, which has been introduced by Chan et al. 2016, and also transformer-based model by Tong et al. 2018, and also another work about hybrid attention CTC 2016-17 by Kim and Hori. So RNN, I will describe briefly about this model. So this is a standard encoder-decoder models that receive the audio representations from the blue part, which is the encoder, and pass it to the decoder and to predict the transcriptions. Similarly, like language model. And then for the transformer model, it removes the recurrence of the RNN and apply attention to speed up the training and inference process. And the work of joint and CTC attention, it leveraged multiple objectives such as CTC and attention decoder, and also it applies RNN-LM to make the prediction much better, similarly like ensemble model. Now we describe and we propose the model that we have for this work, which is low-rank transformer, a lightweight and efficient transformer. So we introduce a new paradigm called low-rank transformer, which is a new in-training conversion method for transformer. We designed the LRT by taking the idea of the autoencoder that compresses the high-dimensional data inputs into a compressed vector representation. And it goes back to a high-rank matrix to learn latent space representation of the high-rank matrix. So we can learn a very compact representations of the distribution of training data, but we also preserve the performance when we try to compare with the large models. And our objective in this task is to predict graphemes by given the audio inputs. So this is our overview of our proposed model. We use VGG encoder as our feature extractions. And also we have a components. If you see from the picture, it's similar to transformer model, but there's some distinguished differences, such as LRFF and LRMHA, which is the low-rank version of multi-attention and feedforward networks. So let's start with the fundamental building blocks of our model, which is we call linear encoder-decoder, or LAD in short. So each M times N matrix can be approximated by the multiplication of E and D, which we call encoder units and decoder units. And basically it learns similarly like autoencoder. So it compresses the high dimensional data inputs into a compressed vector representations. And it decodes back to a high rank matrix to learn the latent space representation of the high rank matrix. So if we have a really small R compared to M and N, our model will have less parameters. We have a better generalization because we remove those bottlenecks in the operations. And also we have a faster training and inference because we have less flops, as we mentioned before, for the low rank metric factorization properties. And this is one of the component we have is called a LowRank feed forward. We have two LED units with additional residual connection to alleviate the gradient vanishing issues. And we also add layer normalization for regularize the models. Also, we have another component, which is important, which is called multi-head attentions. Um, a low-rank version of multi-head attentions. And we also utilize LED units to have faster Q, KV projection. And this is the equation that you can check that we use in the operation. And we also added a residual connection to avoid gradient issues and also layer normalization, similarly like before. Now I will describe the experimental setup. We use two standard benchmark Chinese data sets in speech recognition, AI shell and HKUST. They are multi-accent and conversational telephone Chinese recognition data sets. As our baseline, we set up 3 different transfer model size, small, medium, large, and also we, for our LRT, we try to make sure that we have the same parameters so we can compare with these baselines. In the training phase, we concatenate all characters from our corpus and we add additional spatial tokens, padding start of sentence and EOS, end of sentence. And our model consists of 2 encoded layers and 4 decoded layers. And you can see from our paper for the details of our hyperparameters. And we select the same parameters for LRT with R equals to 100, R equals 75, and R equals to 50. In the inference time, we have a standard beam search decoding and using a beam size of 8. And then we tested the model in GPU and also the CPU cores. Let's come to the result analysis. So from the AI shell 1 dataset, we have interesting results here to show. Our LRT has a lower CER or character error rate compared to uncompressed models. And you can see that with a 60% compression rate, we still achieve a better performance, which is impressive by preserving the information, but also make the model faster in training and inference time. And also the same thing for HKUST dataset, we have the same trends. It means that our model can generalize well in different cases, different style of the voice of the datasets, which is interesting. And also we try to analyze even more from the memory and type efficiency. You can see from the table that we can achieve 1.35 times faster in GPU and 1.23 times speed up in CPU, which is very good for compression models. And we want to show you the training convergence. Our LRT model is able to train very stable and also converge faster in just around 15 epochs, while uncompressed model needs requires more epochs. And also we achieve lower training and validation loss, as you see from the picture. Let's wrap up our presentation and let's go back to the question that we have in the beginning of the presentation. Can smaller model perform better than larger model? The answer is yes. With a smart approach, we not only perform better, but we also have faster models. The second question, how to compress model without any performance loss and how to speed up the training inference process? The answer is in training compression, or we can say is LRT is our model. And let's wrap up and this presentation and conclude. Our LRT model is memory efficient and also fast neural architecture that eliminates the memory and time bottlenecks. And our model can generalize well on different test sets, while also we reduce the number of parameters by 50%. And our model is really fast to converge compared to uncompressed models, which is very useful and practical for industry and also academia for further research. So thank you for your attention, and we welcome any questions that come up to your mind. Thank you.